Welcome all of you to the post-lunch session of today's workshop. Yesterday, Professor Jarkko Kari had presented on the topic of survey of classical cellular automata theory, which was a wonderful talk. Thank you, sir. And today, the topic of Professor Kari is decidability in group cellular automata. Now it's over to you, sir.
Thank you, Sumit. It's very nice to be here again. Yeah, I should mention that I would have really have loved to visit India. But even virtually meeting you is nice. Of course, it would have been much nicer to meet you in person. But what can we do? Okay, so let me share my slides. Just a second. All right, so this is the title of my talk today. So this will be very different from my talk yesterday, because yesterday I talked about classical old things. I mean, most results were from several years ago. But today I will talk about more recent research that I have been doing. And this is done in collaboration with Pierre Beaur from the University of Paris-Saclay, who was doing an internship with me on this topic. And so I will be talking about group cellular automata. And I should, at the very beginning, I should make sure that there's no confusion about this title, because I realized that there are also papers where group cellular automata are used synonymously to reversible cellular automata. But in my case, this term does not refer to reversible cellular automata. So we had a very nice talks this morning by Kamalika about the reversible cellular automata, checking reversibility, and so on. But my group cellular automata are cellular automata where the state set is a group and the cellular automaton is a group homomorphism. And so I will call these group cellular automata. And these particular instances of group cellular automata are linear cellular automata that Sukanta mentioned yesterday. So in linear cellular automata, we have like a ring structure on the states, and the cellular automaton is a linear function on the ring. So group cellular automata generalizes these concepts to arbitrary groups. I will define these concepts in a moment. Just wanted to clarify that this is not about reversible cellular automata, but cellular automata where we have a group structure on the state set. All right, so as before, as we have a finite state set, let's say, for example, these two states. And then we talk about d-dimensional configurations, which are just colorings of d-dimensional infinite grid by the states. So here is a part of a two-dimensional example of a two-dimensional configuration. I will also talk about finite patterns. So a finite pattern is a coloring of some finite collection of cells. Or we have a finite subset of the grid, and we assign states to this subset. We call this subset a shape of the pattern, and this coloring is the pattern. So here is an example of a pattern of size 5. And now, in symbolic dynamics, people talk about subshifts. And the subshifts are it's a subset of the configuration space where you take only configurations that do not contain some specified forbidden patterns, finite patterns. So we have some collection P of finite patterns that we don't want to have in our configurations. We don't allow them. And this specifies a subshift. The subshift contains all the configurations where none of these forbidden patterns appears in that configuration. And this will be a relevant concept also in this talk. And so in the general definition of subshift, we may be forbidding an infinite number of patterns. But if we forbid just a finite number of patterns, we are talking about so-called subshifts of finite type, or SFT. So for example, let's say that I forbid these 4 patterns. Okay. So it will specify a subshift of finite type. And clearly, if I forbid these 4 patterns, I'm saying that 2 neighboring cells are not allowed to have the same color. So I cannot have red and red next to each other, neither horizontally or vertically next to each other, and I'm not allowed to have blue and blue next to each other. So the only allowed configurations that remain are the checkerboard configurations. So in the subshift that forbidding these 4 pattern defines, I only have the checkerboard configurations. Okay, so that's just an example of a subset of finite type. All right, and then obviously we will be talking about cellular automata. So cellular automaton, as you know, is specified by a local rule. So you have a finite neighborhood, and then the local rule that gives you the new state of a cell based on the neighborhood pattern that you see around that position in the previous configuration. Now, here the cellular automaton is defined for all configurations, but we can also talk about cellular automata restricted to some subshift. So let's say that in your space you don't have all configurations, but you only have configurations where some patterns don't appear. So a subshift. And so in the same way, you can define a local update rule, and you can apply it in the cells. You just have to make sure that none of the forbidden patterns appears once you apply the cellular automaton local rule everywhere. And if that doesn't have, if the forbidden patterns don't appear, then you really have a transformation of the subshift to itself. So we call this a cellular automaton on subshift X. So it kind of generalizes the concept of cellular automaton on the whole configuration space. Okay. I will extensively use space-time diagrams of cellular automata. So I will space-time diagram of a d-dimensional cellular automaton is a d plus 1 dimensional configuration where we have one more dimension for the time direction. So you take an orbit of your cellular automaton, you kind of a sequence of consecutive configurations under the iteration of the CA, and then you stack these configurations on top of each other, one after the other, in that new dimension that you have. So you get a space-time diagram. So really, and notice that my space-time diagrams are always bi-infinite. So I don't have a starting configuration. So I start with a bi-infinite orbit without time 0. So the time runs from minus infinity to plus infinity. So I just take a sequence, any sequence of configurations that I obtain by iterating the cellular automaton. And then by drawing these one after the other, I get a d plus 1 dimensional configuration. So coloring of the infinite d plus 1 dimensional grid. Okay. And you certainly know this concept of space-time diagrams for one-dimensional cellular automata, because then you have the space-time diagram is just a drawing on the plane, where the vertical direction is the temporal direction. And notice that for any cellular automaton, the set of valid space-time diagrams is actually a subset of finite type. It's a d plus 1 dimensional subset of finite type, because so we only have a, not every d plus 1 dimensional configuration is a space-time diagram, obviously. You must have the local rule of the cellular automaton respected in each position, right? And so if we forbid all patterns that indicate an incorrect local rule, so you forbid for any pattern P, neighborhood pattern P of the cellular automaton, you forbid this kind of a pattern from your space-time diagram. So you forbid incorrect value underneath such pattern P. Then any configuration where you don't have such invalid patterns is actually a space-time diagram. If you don't have any such pattern, then obviously in each position at all times, the correct local rule was applied. You see? So you have just to forbid these finitely many patterns, and then the valid configurations, D plus one-dimensional configurations, are precisely the space-time diagrams of your cellular automaton. So I will denote this subshift by STF. So F is the cellular automaton and STF is the set of space-time diagrams. And now if you are looking at the cellular automaton over subshift, then on top of these forbidden patterns, you also add in the horizontal direction the forbidden patterns that define X, that are forbidden in X. And this way you also get the set of space-time diagrams for cellular automata over subshift X. It's also a subset of finite type in one higher dimension. Okay. And this way, this is interesting because this means that many questions about D-dimensional cellular automata become really questions about D plus one-dimensional subshifts of finite type. So if you have some algorithms to solve questions about the D plus one-dimensional subshifts, then you usually can use those algorithms also to solve questions about D-dimensional cellular automata. That sounds nice because the subshifts are static objects. You don't have any more dynamics. It's a static drawing in the D plus one-dimensional space. But unfortunately, it doesn't seem to help much because it turns out that pretty much everything is undecidable about subshift of finite type already in dimension 2. And so this way, so we are reducing dynamics of one-dimensional cellular automata into subset of finite type in 2 dimensions, but everything is undecidable. Pretty much everything is undecidable about such subshifts. These are so-called tiling problems. So it doesn't seem to be helping much, right? You are not getting algorithms from there because questions are undecidable. But we still can use this approach if we somehow limit the type of subshifts that we are considering. So if we, instead of considering all subshifts of finite types in 2 dimensions, maybe we somehow restrict the situation to somehow so that we do have algorithms, that we have decidability. And this is exactly what I will be doing in this talk. So I will be considering only subshifts where we have certain algebraic structure, namely a group structure. And then it turns out that we do have algorithms to handle such situations. So in the following, the state set will be a finite group. So for example, integers modulo n under addition, that would be an example of a finite group. That would be a commutative group. But there are many other finite groups also. As you probably know, group theory, finite groups are quite rich bunch of objects. And now once you have a group structure on the states, you automatically get also a group structure on configurations. So where you just apply the group operation cell-wise. So you can add or multiply in the group 2 configurations so that you just multiply the values in each cell separately. So we have a group structure on this set of configurations. And now we can define the group cellular automata and group shifts. So we say that a subshift, a subset of this configuration space defined by some forbidden patterns, is a group shift if it is closed under the group operation. So it is a subgroup. So if you multiply two configurations that belong to the group shift, also the result after the multiplication is in that subshift. So it's closed under multiplication in the group. And we say that the cellular automaton, either on this whole configuration space or some group shift inside it, we say that the cellular automaton is a group cellular automaton if it is a homomorphism. In other words, the product of the image of a product of two configurations under the cellular automaton is the same as the product of the images. So the image of the product is the same as the product of the images. Okay, so this is my definition of a group cellular automaton. And now it immediately follows that if you have a group cellular automaton and you look at its space-time diagrams, it is a group shift. So if you take a valid space-time diagram and another space-time diagram of a group cellular automaton, and then you multiply them, you get a valid space-time diagram also of that group cellular automaton. That's because of this homomorphism property. And so if you have now algorithms for group shifts, you can use these algorithms on this space-time diagram, set of space-time diagrams, to get algorithms to solve various questions about the group cellular automaton. All right. And the good thing is that we do have algorithms for group shifts. They are simpler objects than arbitrary shifts. The group shifts are much easier to handle by algorithms than arbitrary subshifts of finite type. And this is already known for a long time. So these results are based on these very nice properties proved by Kitchens and Smith already in 1989. And I have two important properties that every group shift has that we can exploit to obtain algorithms. So first observation is that every group shift is automatically of finite type. So in the definition of group shift, I didn't say that it has to be a finite type. So it could be basically defined by forbidding an infinite number of patterns as long as the resulting set is a subgroup. So it's a group shift. But it turns out that it always can be then also defined by forbidding a finite set of patterns. So all group shifts are of finite type. And the second property is that periodic configurations are dense in group shift. And let me explain what it means. It just means that if you take any pattern which appears in some configuration of the group shift, then this pattern also appears in a periodic configuration. So all patterns of a group shift are present in periodic configurations of the group shift. And this is a property that is not true at all for arbitrary subsets of finite types. We even have a subset of finite type which do not contain any periodic configurations. These are so-called aperiodic tile sets, let's say. But here in group shifts, periodic configurations are dense. Every pattern belongs to a periodic configuration. And using these two properties, we can design algorithms for group shifts. So here I just remind you of these two properties, and I will give you some algorithms. So first algorithm tells you whether, if you are given a finite pattern, we can decide, we are given a finite pattern and we are given a group shift. Group shift is given in terms of its forbidden patterns. Then we can decide if this pattern appears in some configuration of the group shift. Okay. So notice that, of course, when you are forbidding some set of patterns and defining a SF subset of finite type in this way, there are also some other patterns that get forbidden by this fact. And in general, for arbitrary subsets of finite type, we cannot, there's no algorithm to tell for a given pattern if it got forbidden or not. But for group shifts, we can actually tell if a pattern appears in the group shift or not. I have here a small argument for that. Maybe I can briefly tell this, even though it's a bit technical maybe. But this is really a standard argumentation already by Wang. Wang was a logician who worked, a very famous logician, who also introduced so-called Wang tiles and worked on computability theory, also on tilings, let's say. All right, so this is how the argument goes. So you are given a pattern P that you want to test if it appears in some configuration, and then you are given also the finite set Q, which are the forbidden patterns that define a group shift. And now we kind of run two algorithms in parallel. On one side, we are looking for a proof that P appears in the group shift. And on the other side, we are looking for a proof that P does not appear in the group shift, in any configuration of the group shift. And we know that one or the other proof exists. So how do we look for a proof for a positive instance that P appears in the subshift? Well, we use this property 2 here, that periodic configurations are dense. So we know that if P appears in some configuration, it will also it appears in some periodic configuration, because periodic configurations are dense. So we just start to enumerate periodic configurations for bigger and bigger periods. Okay, so for each period, you have only finite number of periodic configurations with that period. And so you just keep on increasing the period and enumerate all periodic configurations. It doesn't matter in which order you do that, but you just have to enumerate all of them. And for each periodic configuration, you check whether P appears in it and none of the forbidden patterns in Q appears it. And if you find such a periodic configuration, then you know that P is present in the subshift because you found a proof of it. You found a periodic configuration that's in the subshift because it does not contain any of these elements of Q, and it contains P. Right? And so this is the kind of proof that you look for positive instances to see that, to prove that P is in the subshift. And for a proof that P does not appear in the subshift, this actually works for any subset of finite type. So we just look for all finite patterns for bigger and bigger squares until we find a number n such that every n by n square that does not contain a forbidden pattern of Q, none of the, such that each of these square patterns that contain P, let's say in the center of the pattern, also have a forbidden pattern from Q. And so you know that at that moment, you know that you cannot have P in the subshift because it cannot appear in any n by n square without actually forcing also one of the forbidden patterns in the square. All right, so you run these two, we call these semi-algorithms, in parallel, and you know that one or the other will eventually stop and find the proof that P is in X or that P is not in X. It's a kind of a standard argumentation in this field. All right, so we can decide if a pattern appears in a given group shift, but the main point for me from this is that now you can test if somebody gives you two group shifts, we can test if they are identical, if they contain exactly the same configurations. Namely, so suppose somebody gives you two group shifts, xq and xp. Q and P are finite sets of forbidden patterns. And now what you do is that you check for each forbidden pattern in P whether that pattern appears in xq. And we can do that because by this algorithm that I just discussed previously. So for any element in the set P, any pattern in P, we can test whether it appears in some configuration if xq. If none of them appears in xq, then we know that forbidding these elements in P does not forbid any of the elements in xq. So xq is a subset of xp. So we can test whether xq is a subset of xp just by running through all the patterns in P and checking for each that it's not in xq. All right, and then we reverse the roles and we test the other way whether xp is a subset of xq by the same procedure, and then we have tested for equality. All right, so we can test for two group shifts if they are the same or not. So you're just giving the forbidden patterns and you can tell if they admit the same set of configurations. All right, and so now how do we use these algorithms? So the main technical contribution that we have is that you can algorithmically slice like lower dimensional projections of any group shift. So if you have let's say somebody gives you a two-dimensional group shift, and now you are interested in the set of all horizontal strips that you have in the configurations of your group shift. So we say that it's a one-dimensional, it's the projection, one-dimensional projection in the horizontal direction. All the slices like this that appear in configurations that are in your group shift. Now the set of these slices is a one-dimensional group shift. It's closed under group operation because the original subshift is closed under group operations. And what we prove is that you actually can construct it. There's an algorithm to build it. So somebody gives you the two-dimensional group shift, and our algorithm will then be able to produce the forbidden patterns that define these slices, the valid slices, horizontal slices. Okay. And yeah, as I said, the projections are also group shifts. They are lower dimensional group shifts. And we can do this in any dimension, not just from 2 dimensions to 1 dimension, but you can go, let's say, from 9-dimensional space into the 3-dimensional projections or whatever. They all can be effectively algorithmically computed. And we will apply this to the space-time diagrams of a group cellular automaton. So remember that the set of valid space-time diagrams of a group cellular automaton is a group shift. And now if you, let's say, you take a vertical projection, so you take all the valid sequences in the vertical direction in your space-time diagram. Well, these are exactly what we call traces of cellular automata. It's the trace subshift. It contains all the sequences, temporal sequences of states that you can have in some orbit of the cellular automaton. Right? So temporal sequences of states in one cell is a trace, and all possible temporal sequences is the trace subshift of cellular automaton. And so we can construct this trace subshift effectively for any group shift, any group cellular automaton. So this was a projection in the temporal dimension. Now we also can take the projection in the spatial dimensions. And this is exactly what is known as the limit set of a cellular automaton. Okay, so remember that my space-time diagrams are two-way infinite. So the time runs from minus infinity to plus infinity. So horizontal slice here is a configuration which has an infinite sequence of pre-images. Right? It's not the Garden of Eden because it has a pre-image. It's not the Garden of Eden for 2 time steps or 3 time steps. It has an infinite sequence of pre-images because it's a configurations in a bi-infinite orbit. And this is called the limit set of the cellular automaton. All such configurations that have an infinite sequence of pre-images is a limit set. And so we can effectively construct the limit set for any group cellular automaton. So if you give me a group cellular automaton, the limit set will be a group subshift. It's a subshift of finite type, and I can effectively construct a finite number of forbidden patterns that defines this limit set. And now the good news is that once you know the trace subshift and you know the limit set of a cellular automaton, then we can pretty much decide everything about the cellular automaton. We can test whether it is injective, surjective, nilpotent, periodic, equicontinuous, sensitive, and so on. I will show you examples of how we use this trace subshift and limit set to decide these things. So pretty much all these properties becomes decidable, and this is in any dimension of the space. And even if the group cellular automaton is not on the whole configuration space, but it's a cellular automaton on a subshift, even then all these properties are still decidable in any dimension. Yeah, so let me note that I already mentioned this in the very beginning, but let me remind again that this concept of group cellular automata is a generalization of the concept of a linear cellular automata that Sukanta mentioned yesterday. And there have been many works over the past 50 years proving that various properties like injectivity, surjectivity, and so on are decidable in maybe dimension 1, dimension 2, and so on for linear cellular automata. So these results that we have, they really generalize these old results about linear cellular automata. Okay, so in a linear, like I said, in a linear cellular automaton, your state set or alpha, the state set is a finite ring or a field, and your local rule is a linear function in that case. So the cellular automaton is a linear function. And slightly more general is the so-called additive cellular automata, where your state set is a finite commutative group, and your cellular automaton is group homomorphism. But so in our case, the group does not need to be commutative anymore. So let me, as an example, maybe show you how we can decide now injectivity and surjectivity. So let's say, just to remind you of the definition, So a cellular automaton is called injective if different configurations have different images. So every configuration has at most one pre-image. And it is surjective if every configuration has at least one pre-image. And this can be defined on any subshift X, but you can, if you like, you can just think of in place of X, you can take just the whole configuration space. But this works also on subshifts. And we know, as we have seen in the nice talks this morning, that these properties can be decided for one-dimensional cellular automata. In fact, they can be decided on one-dimensional cellular automaton over any subshift of finite type, not only on the whole configuration space, but even on any SFTs. And in 2 dimensions and higher dimensions, I proved 30 years ago that these both questions are undecidable, even for the full shift. All right, and so I claim that for a group cellular automaton in any dimension, these are both decidable. Let's see, for surjectivity, we decide surjectivity as follows. So notice that the cellular automaton is surjective if and only if its limit set is the whole space. So limit set, remember, it was the set of configurations that have an infinite sequence of pre-images. Now, if your cellular automaton is surjective, then every configuration has a pre-image. So then you can, of course, iterate this backwards in time. So you have every configuration has an infinite sequence of pre-images. And so the limit set is the whole space, configuration space, or subshift X if you are working on a subshift X. And if you are not surjective, then you have a Garden of Eden configuration. So clearly the limit set is not the whole space. And now I told you that in a group cellular automata, we can effectively construct this limit set. It's a group subshift, and we can algorithmically construct it. And now I also told you that we have an algorithm to test if 2 given group subshifts are the same. So we have an algorithm to test whether this limit set is the same as the space X. And that's exactly surjectivity. So very simple. We have an algorithm. Right? We construct the limit set and we test if it's the our whole space or our given group shift. For injectivity, the situation is almost as easy. So of course because we have a group homomorphism, for injectivity, it's enough to test that the unit element of the group has only one pre-image. So this is called the kernel of a homomorphism. The set of elements that are mapped by F into the element 1, the identity element of the group. Right? I will denote like this. So 1G is the identity element of my state set, which is a finite group. And then this is the configuration where in every cell you have 1. Okay. And now the pre-image of this single configuration, this identity, is the kernel, and it can be effectively constructed. It's again a group shift because you just forbid. What do you forbid? You forbid every neighborhood pattern which is not mapped into 1. Any neighborhood pattern that is mapped into a state different from 1 must be forbidden, because then configuration containing that pattern is not in the kernel. So you just forbid those, and that defines you the kernel of the homomorphism. So we can construct the kernel, and now we just check whether the kernel of the homomorphism is this singleton set. And that's equivalent to injectivity of the homomorphism. Homomorphism is injective if and only if the kernel only contains this identity. And these are both group shifts, and again, identity can be tested. We have an algorithm for testing it. So we have injectivity, algorithm to test injectivity. All right, some more examples. Properties. These are properties that are undecidable already for one-dimensional usual cellular automaton. So a cellular automaton is called nilpotent if its limit set only contains a single point. In other words, all the orbits, I mean, no matter what initial configuration you choose, after some time, you only have one configuration that's possible. Okay, and the cellular automaton is eventually periodic if the map starts to repeat itself after some time. So there's some period P such that after some time N, you start to repeat with period P. No matter what your initial configuration was, you start to repeat with period P after time N. And it is periodic if it's directly periodic. So you return to the initial configuration after some time P, no matter what is your initial configuration. And so we know that these are all undecidable for one-dimensional cellular automata. But what about group case? I claim that these are actually decidable. So there's an algorithm to test all three properties in any dimension, and even if we are not in the full shift, not in the set of all configurations, which we call the full shift, but on a subshift, group shift X. So let's see. Nilpotency is very easy to test now. Remember, we can construct, if F is a group cellular automaton, we can construct the limit set. And then we just test, is it the same as this singleton set? And this is a group shift also. An identity of two group shifts can be tested. Okay, so we have an algorithm for nilpotency. Just because we know the limit set, we can test nilpotency. What about eventual periodicity? Well, eventual periodicity we can test using the trace subshift, the temporal sequences, because if a cellular automaton is eventually periodic, it means that you only have a finite number of different traces. Okay, so we construct the trace subshift, which is a one-dimensional SFT. And now in one dimensions, we can easily test using some standard algorithms. We can test the finiteness of a subshift of finite type, whether you have just finite number of configurations remaining. So we construct the trace subshift and we test whether it is finite or not, which can be done. So that's an algorithm for eventual periodicity. And now periodicity, well, a cellular automaton is periodic if and only if it is reversible and it is eventually periodic. That's easy to see. And now we already have seen algorithm for both of these properties. We have seen injectivity tested on my previous slide, and we have seen eventual periodicity up here. So we can test periodicity. You see, so we have these three algorithms for nilpotency, eventual periodicity, and periodicity. Now we also can test some dynamical system-like properties, sensitivity to initial conditions or equicontinuity, which is also rather different from normal cellular automata, unrestricted cellular automata, where both properties are undecidable. So I didn't really have time yesterday to define these concepts precisely, but just briefly, a cellular automaton is sensitive if you have an observation window such that any configuration can be modified arbitrarily far away in such a way that that modification will eventually be seen in your observation window. So changes to your initial configuration propagate. Your initial configuration can be changed in such a way arbitrarily far that your modification propagates to your observation window. And equicontinuity is a kind of the opposite end of the spectrum. So in equicontinuous CA, no matter how large your observation window is, modifying your configuration far enough will not propagate in your observation window. And there's a kind of these are the only two possibilities that you have for a group cellular automaton. It is either sensitive or it is equicontinuous. In general cellular automata, we have also in between the case of almost equicontinuous CAs. Those where on some configurations you have sensitivity and on some configurations you have equicontinuity. But in group cellular automaton, it turns out that either you have sensitivity on all configurations or you have equicontinuity on all configurations. There's no middle ground, basically. And now it's known that a cellular automaton is equicontinuous if and only if it's eventually periodic. I mentioned this yesterday. Only trivial cellular automata, eventually periodic cellular automata, can be equicontinuous. But that means that we have an algorithm for equicontinuity because we have an algorithm for eventual periodicity. I gave you an algorithm on the previous slide. So we can test equicontinuity. And if we can test equicontinuity, it means that we can test sensitivity because it's just a complement property. So if your cellular automaton is not equicontinuous, then it's sensitive and vice versa. So we have an algorithm for sensitivity also, which is very different from non-group cellular automata. Mixing properties, I didn't talk about this yesterday. This is another kind of another family of properties that people are interested in the theory of dynamical systems, whether your configuration space gets mixed when you iterate the cellular automaton. And here, this is the only question that we couldn't answer with our method directly yet. So we don't know whether transitivity or mixingness, which actually turn out to be an equivalent property for group cellular automata, they are transitive if and only if they are mixing. So two flavors of mixing properties. We don't know whether there is an algorithm to test this property, transitivity or mixingness. Okay, we only have a semi-algorithm, which is a kind of not satisfactory. It would be nice to have an algorithm. So there's something for future work here to try to find an algorithm also for transitivity for group cellular automata. And again, it's known that mixingness and transitivity are undecidable for general unrestricted cellular automata. So, all right, so I'm ready to finish here. So I just want to point out that all our results are very heavily based on this important results by Kitchens and Smith from 1986, namely the properties of group subshifts. And now based on these results, we were able to design algorithms for a number of properties for arbitrary group cellular automata. Notice that we have not discovered any undecidable property yet. So for all questions that we looked for, either they were decidable or, like in case of transitivity, we don't know the answer yet. But so I wonder if there is some general theorem that would state that pretty much, in some sense, everything concerning group cellular automata would be decidable. Everything here in has to be made more precise what it means, but it seems like pretty much everything is, there's an algorithm for everything, more or less everything. But for transitivity and mixingness, as I said, we don't know for sure. I suspect that there is an algorithm, but we were not able to design one directly with this method. And I also want to point out that, like I said, there's a lot of papers in the past about algorithms for linear cellular automata and additive cellular automata in various setups for various questions that I have talked about here. So this our method more or less unifies all these papers, all these results into a single proof that covers both linear cases and additive cases. But at the same time, I have to say that, of course, the algorithms that I have presented here are not really practical algorithms in the sense that their complexity can be very bad. We were mostly interested in the borderline between decidable and undecidable to see that, at least theoretically, there is an algorithm, even if the algorithm is maybe not very practical. Whereas these papers, or these old papers for linear cellular automata and additive CA, they usually provide actually very practical algorithms. They tell you exactly how from the coefficients of your linear local rule you can tell whether the cellular automaton is injective or surjective or so on. So they provide much more practical algorithms than our method. All right, so I will finish here. I'm a bit early today, unlike yesterday when I was late, but I'm ready for questions. Thank you.
Thank you, sir, for this wonderful talk. Anyone have any question regarding this talk? Any questions?
Yeah, I have one question. See, when you are talking about group CA, I mean, my question is, your group CA automata can be reversible in any case?
They can be reversible. They can be reversible, not that they can be non-reversible. Yeah.
Okay, but you're talking about the limit sets. You can always find the limit sets. So that I can understand. So you are getting limit sets. So we generally get limit sets for non-surjective cellular automata. But in this case, we are getting limit set, but it's reversible. So how it is related? These things related.
Well, if the cellular automaton happens to be reversible, then the limit set is just the whole configuration space. Yeah, so you can have the limit set that just then happens to be the whole space. Okay. But it exists, but it's a whole space. Yes.
Okay. Yes. Then also.
And if you are not if you are not surjective, then the limit set is something. It's a strict subset. It's not the whole space, but it's a subset. Yeah.
So here the linear cellular automata, as you have said in conclusion also, linear cellular automata, which are studied in over years, as well as additive cellular automata, both are group cellular automata in this case, right?
Yes, they are special cases of group cellular automata. So in additive cellular automata, you have a commutative group, like usually the cyclic group. You have modulo n addition. That's the most common group that people have looked at in the linear case, right? But so in our case, the group can be any finite group.
There is another class of CA in some literature we find called complementary CA, where the rule is just complementation, negation of the of some linear rule, right?
Okay. Yes.
So in that case, will that be the group cellular automata?
So actually, that would then that would not be any more group. So if you complement it, then it's not any more a group homomorphism. That's right. So.
But what is observed, especially for the binary cases, say using matrix algebra and vector algebra, we can classify, we can characterize. Especially, I'm talking about the linear cases, especially. So sorry, I'm talking about the finite case. But what is observed, a few researchers proved that using that, matrix algebra and some vector space theory, etc., they can characterize this kind of complemented CA. So they are not linear, but that they have named it not linear also. They have named it complemented. So they are very close to linear system. So in this case, they are not group. In your case also, I mean, these kind of cellular automata, although they are very close to group CA, linear cellular automata, but they are not group cellular automata, right?
Yes, you're right. That's our case would not cover those results. And yes, I know that. So it's like an affine map. It's not a linear map, but it's an affine map. And yes, they are not. It's not a homomorphism. So it would be nice to see if somehow our method could be also extended somehow by allowing that the map not to be exactly a group homomorphism, but like a something similar affine map. But we have not done that. Yeah.
Thank you. Thank you. We have enjoyed your talk. So many things. Any more questions?
Any other questions? I think there is no other questions. Thank you, sir.
Okay.
Thank you for
Thank
this.
you. Thank you very much.
Thank you, Jarkko, for your effort and coming over here and giving the giving the talk.
It was my pleasure.
We all have enjoyed.
It was my pleasure. Very nice. And the conference still continues, so I will be watching the talks also in the coming days. Yeah. All right. So I will see you tomorrow then. Yeah.
Okay.
Yeah.
Now
All right.
we are
Bye.
ending this session and as well as today's workshop. Thank you everyone for joining. We will meet up again tomorrow at 10:30 p.m. Thank you all of you.